Okay.
There you go. So basically, I'm a confirmed lunatic. I've been doing this for a very long time now, 45 years in all these different fields, and I love what I'm seeing today. I love seeing the renaissance of what we beat our heads against for so very long, and it looks like it's starting to come to fruition. This is one of my graphics in our group's graphics regarding industrial activity on the moon. There's three types of science in the NASA world. We call them the von Braunians, the O'Neillians, and the Saganites. The Saganites are look but don't touch. The von Braunians are the state uber alles, let's explore the galaxy. And the O'Neillians, which I am more of a part of, are the ones that we want to take the commercial world to space for the good of all humankind. And this is something we're looking at for, this is a vacuum induction furnace. Vacuum induction furnaces work real good in a 10 to the minus 12 torr vacuum. Industrial robots, industrial systems. This is a gantry crane. I have a contractor paper that we did for lunar surface systems, the whole history of it, and actually doing industrial types of things on the moon, because it's much more than science. Science is a great driver, science is a great adjunct, but science is not going to give us what we need for the economic development of the solar system. This is what I'm currently working on. This is an in-space manufactured spacecraft that we call the Starcraft. Much lighter, much more capable than current systems because, believe it or not, satellites are moving towards larger satellites. Look at the first Starlinks versus the Starlinks that are flying now and the next Starlinks that will be flying. So space-like stuff are big. This is one of our iterations of our own orbit assembly facility that we call the Starport for actually building ISAM stuff, and our good friend Bryce over here helped us out with some of this work. We're doing a lot of stuff. Now, prior flights, my gig and what I'm talking about today is that we love all this robotic stuff. We're doing all of it on the ground right now. All of these computers, everything that we're doing, all this cool stuff on the ground right now, we got to make it work on the moon. We got to make it work in deep space. And that has been the lag for the past 40 years in the aerospace industry. And this is what I've also beat my head against. In 2021, we flew the Intelligent Space Systems Interface to the International Space Station as a TRL-7 demonstration. It's a robotic connector from our German friends at iBoss GmbH. That has power, communications, and mechanical connections so that we can connect, disconnect, put things together in a modular fashion. We flew this to ISS, but we also, at the same time, this is on the Kibo external facility. We were out there for 9 months, but we also flight qualified some computers and new technologies, operating systems in space. We also, and this was just a few months ago, this is the flight server. This is the world's first server that landed on the moon. It's based on the microchip PolarFire system on a chip. It worked just fabulously from low Earth orbit all the way to the moon. It worked in lunar orbit, and unfortunately we ended up on our side again with IM-2. The last telemetry reading we got was minus 67.9 degrees C before IM-2 died. We flew an 8 terabyte SSD from our friends at Phison in Taiwan. We're partnered with them. We were able to obtain telemetry regarding the performance and the radiation environment of all this hardware. Test engineering is how we're going to make this happen. Test engineering is probably just as important as any other thing that we are doing in space, because we got to make this stuff work. This is what we currently are about to fly. We just put this together. This is a VPX for those of you who are double E's. The VPX is a great small form factor computer system. We have a PolarFire that we reimagined with a Jetson Nano. So if you want to run your robotics, we're flight qualifying the Jetson Nano for several different environments in space. We have right here, this is a 166 terabyte SSD card that we're going to be flying. We will be able to have some AI modeling on this system, and then we have the overall controller, power control, again, another PolarFire, really nice hardware from Microchip, and we have flown it in many different space environments and it's worked really well. Our next is going to be based on what's called the HPSC, which was funded by NASA to Microchip for $50 million. This board is in development right now, along with a Jetson Nano AGX. We're going to be the first to flight qualify that hardware. And so if you really, really want to play with your robots in space, we have some toys for you. So again, and then we will be upgrading this board. On a single board, we'll have 566 terabytes of storage, SSD. We'll be able to go over a petabyte in a box, along with the HPSCs and the PolarFires for our different types of activities. This just shows different power supplies, the VPX architecture that's very well suited for the space environment. Again, it's all conduction cooled, so it's all set up for space. And everything here for the printed circuit boards is conduction cooled. And so now we have a methodology for running all these cool toys in space and providing radiation protection, which is my magic that I will not talk about today. This is a detail on the PolarFire. This 152-pin PolarFire. We have a Gen 3 PCIe switch along with the Jetson Nano, except we're going to delete the fan. Ethernet, dual port Ethernet. The Jetson Nano also has everything is 1000 base T Ethernet, so plenty of bandwidth, along with PCIe Gen 3 on this one, and then upgrading to PCIe Gen 4 and Gen 5 as we move up. This is the flight hardware that we flew to the space station. This is after we got it back in 2023, so we were able to tear it down. We were able to analyze everything. The PolarFire with its radiation protection and conduction cooling all together with the power board as well. Again, another picture of that. This is the new toy that's coming out with the Microchip. We'll have 32 gigabytes in two different banks, two 32 gigabit banks, along with the MRAM. We're going to have that along with the PCI PFX switch, the Jetson Nano AGX, along with 25 gigabit per second optical. I can't tell you exactly which mission we're flying this on, but we will be doing the first multi-laser constellation demo utilizing baseband communications to bridge across multiple laser communications constellations. Again, the Microchip part, how it all puts together, the different parts, so we will have advanced communications, very up to 25, and we can aggregate to 100 gigabit per second. The time-stamped networking that JPL has developed, that they're working with Microchip on for the HPSC, will be able to do very high bandwidth communications and architecture. So that's just all the different toys we have right now. That is in layout, and we expect to go to production on this in September or October. Really, really nice hardware, and we want to support everybody that's out there as long as our own, as well as our own applications for autonomous navigation in space, as well as on the lunar surface. Now really, I think we should be talking a lot more about how we do autonomous navigation on the moon. There are several different technologies out there that will really help put together let's call it a much more robust methodology than what we're seeing here right now. And actually some of this had been tested at NASA JSC 15 years ago. So there's a lot of cool tech out there. There's a lot of good stuff that we want to do. And it's my proposition that we will not do it without testing, debugging, breaking these computers in space. And this is what we're doing. I can't tell you who our sponsors are right now, but let's just say they're fun people. So I like to do quick presentations and maybe time for a question. So I'm done.